Now, if S and T are monites, then 1s pi is equal to 1t. Means identity of monite goes to the identity of this monite goes to the identity of this monite. Next equation. If a semigroup S is for some X a subsemigroup of tau X, we say that S is a semigroup of maps or a transformation semigroup. A morphism phi from semigroup S into some tau X is called representation S, and phi is called faithful representation. If it is one representation, if phi is 1. Correct? Means if there is a map from S to tau X. Tau X, you know that it is a full transformation semigroup. Is it clear? So a map, a morphism from semigroup S to some tau X is called representation of S. And if this phi is 1, 1, then we say that this representation is called faithful representation. Correct? Now we do result. Theorem 1.1.2, page number 7. If S is a semigroup and X is equal to S1, then there is a faithful representation. phi from S to tau x. So see, what is the theorem? If S is a semigroup and X is what? Monoid, S1. Then there is a faithful representation from S to tau x phi. Yeah, see. Means we have to prove this phi as faithful representation. To prove phi, see what is tau x here? Tau x is what? And it consists of maps, for example, say rho A from X. A is an element of semigroup S, and it's a map from, you say, X to X, that is S1. So tau x is what? It consists of all maps from X to X. X is what? Monoid, that is S1. So what we have to prove? We have to prove that phi is a faithful representation. To prove phi is a faithful representation, we have to prove two things. We have to prove, first thing, we have to define a map from S to tau x. That map should be well defined, of course. After that, after defining a map, we have to prove that phi is a morphism. Morphism means we have to prove it is homomorphism. And phi is 1, 1. So two things we have to prove, that phi is a morphism and phi is 1, 1. If it is so, if we are able to do so, then that will prove that phi is faithful representation. Now let's prove. So for each A in S, define a map rho from S1 to S1 by x rho A is equal to x A x belongs to S1. Thus, x rho A belongs to tau x. Yeah, well, see, we have defined a map like this: x rho A is equal to x A. It's trivial to check that the map is well defined, isn't it? In this book follows something different from other books, that elements are written on the left side of the map. This is the map. In general, most of the authors write elements on the right side, but here element is written as left side, doesn't matter. So we can check by ourselves that the map is well defined. Okay. Now, of course, x rho will go where? It will go x rho A is equal to x A, isn't it? So thus rho A goes in tau x, isn't it? Because it is well defined map. So now define a map alpha from S to tau x by A alpha is equal to rho A, like this. Where A belongs to S. Of course, this map is well defined as rho A is well defined. So this map is well defined. We can check also, no problem. By taking A is equal to B, we can prove that rho A is equal to rho B, no problem at all. Because when A equal to B, x A is equal to xb, x A is equal to xb, it means that x rho A is equal to x rho B, it means that rho A is equal to rho B, it can be checked. Now, we have to prove that it is morphism, and we have to prove that it is 1, 1. Now, let's see, first it is 1, 1. So, phi is 1, 1. So, let A is equal to B, correct? Let A alpha is equal to B alpha. It implies what? Rho A is equal to rho B. It implies when two maps are equal, it means that it is equal at every point. That it means that x rho A is equal to x rho B. Correct? X rho A is equal to x rho B. impose it, what does it imply? XA is equal to XB for every X belongs to S. For every X belongs to S is from where? It is from S1 basically. So XA is equal to XB for every X belongs to S1, and S1 contains identity also. That is, it implies that 1 into A is equal to 1 into B. It implies that A is equal to B. It implies that phi is 1, 1. Correct? Now to prove that phi is morphism, we show that rho A into rho B is equal to rho AB. Okay? Because if we prove this, then automatically it will be proved alpha is a morphism. Now see how. See, for any X belongs to, see, this is a map, this is a map. When we say that two maps are equal, if it is equal for each element, if both maps have same action on each element of domain, that is, for any X belongs to S1, X rho A B, it will be X rho A into rho B, that is X A into rho B. This is what X A into B, this is what X into A B, and this is what X into rho A B. So it means what? It implies what? Rho A, rho B is equal to rho AB. Now, for any AB, alpha is a map from where to where? It is mapped from S to tau X. So for any AB belongs to S, A alpha into B alpha what we have to prove? A alpha is what? This is rho A, this is rho B, this is what? This is rho A B, and this is what? A B alpha. It implies what? Alpha is morphism. It implies what? Alpha is faithful representation. Faithful representation. So in this way we have proved that alpha is a faithful representation. So in next lecture we will start a very important topic that is about articles all about monogenic semigroup. Monogenic semigroup is very important, and very important theorem is I will tell you in the next lecture. So I stop here. Thanks.